You cannot even use the Newton's second law. Okay, it's too complicated to use the Newton's second law to do the calculation. But you may still be able to use these conservation laws. And we're going to have many conservation laws for the energy, conservation laws for momentum, conservation laws for the angular momentum. So here, conservation. Actually, what I mean by the conservation is just this. There are some quantities will not change during the motion. Okay, so that quantity wouldn't change if it's a constant during the motion. We have the conservation law for that particular quantity. But okay, energy. So basically it says that conservation law source says that for any isolated system, the energy will not change. But energy can take different forms. So even the energy, total amount of energy cannot change. The energy can change from one form to another form. Okay, so it will give us the energy conservation laws. Now let's look at how this energy changes from one form to other forms. Here we will give two general equations called the work kinetic energy theorem and conservation of total energy. Then we will give a special case, conservation of the mechanical energy. Okay. So the first one, work kinetic energy theorem, says that if you calculate the work done by all the forces or the net work, it should equal to the change in the kinetic energy. Okay? And the second one, conservation law of total energy, says that instead of calculating the work done by the net force, if you try to calculate the work done by all the non-conservative force. Okay, we mentioned that forces can be put into two categories, conservative force and non-conservative force. Okay, here you calculate all the conservative force and non-conservative force, so you get net work. If you calculate the work done by all the non-conservative force, if you introduce the change in the mechanical energy, okay, and then there is a special case called the conservation of mechanical energy, which is as some system, for some system, in fact later we're going to see this kind of system are called conservative system. For this kind of system, the mechanical energy will not change, so delta E will be 0. You can state this equation in some other way. If delta E equals to 0, the change in the mechanical energy equals to 0. That means final mechanical energy has to be the same as the initial mechanical energy, right? Okay. And because the mechanical energy is the summation of the kinetic energy and the potential energy, so this also indicates that the final K plus final U should be the same as initial K plus initial U. Okay. So it will give us a lot of powerful equations to do the calculation. Okay, now let's try to understand these equations. So you can think about conservation law. Why it's powerful? Because it applies to many different things. For example, you can consider the conservation of your money. Okay, money itself has to be conserved because you cannot print money, so you're not going to create your own money. And by the way, I think you wouldn't like to destroy your money. So your money is basically conserved quantity. And you can see that, but it will take many forms to, you can check that the conservation will lead to many facts. For example, if you think about the money in your account, you may have the checking account and the saving account, okay? And you can transfer your money from the checking account to the saving account or vice versa, okay? But it wouldn't change the total amount of your combined account. So this kind of like what happens for this equation, okay? If you think that the kinetic energy is your checking account, potential energy is your saving account, okay? In fact, it is. Potential energy is potential energy stored, saved there. And kinetic energy is energy exhibited, okay? So, for example, initially you have 5,000 in your saving account, and you have 1,000 in your initial account, dollar, okay? A checking account. And then, for some reason, you want to make increase the money in your saving account to 2,000. Now, of course, in your saving account, how much you are going to have? 4,000. Right? Okay, because you have to. The summation of the two should be the same. Here is 1,000 plus 5,000, 6,000. Here is 2,000 plus 4,000, 6,000. Okay? So this is what happens for this equation. Okay. And similarly, all these equations are talking about the same thing. Like here, you just count the total number. You say, okay, initially combine the two accounts, I have 6,000. Finally, I have 6,000. Nothing changed. I'm just transferring them from one of my accounts to another account. Or if you try to calculate the change in the money from the previous month to this month, you find it's zero. 6,000 minus 6,000 is zero. There's no change. But now, it's just a special case. It assumes that you didn't do any withdrawal or deposit, right? Okay? But now, think about, if initially you have in your saving account, you have 5,000, and in your checking account you have 1,000, okay? And later, you check your saving account and checking account. You find you have 2,000 here and 2,000 here. Okay? So if you try to calculate the change in your total money, okay, you are going to find that finally we have 4,000. Subtract your initial money, 6,000, you get negative 2,000. You lose $2,000. Okay? So what happens? If you go back check, okay, maybe you withdraw 2,000, or maybe the bank goes 2,000 from your account, whatever. They are the work, okay, done by the non-conservative force. Okay. So, because that means anyway, you pull the money out from your bank account, so it makes it to somewhere else, and that kind of money is captured by the work done by the non-conservative force. Okay. And then, basically, when we do the calculation, we are playing these games similarly. So, like here, some money is lost because you do the calculation, or if you can try to evaluate your money, let's say, I don't know how much I have here, but I know last month I have 5,000 here, I have 1,000 here, and then I make a deposit 2,000. Okay, so now I know that I should have 8,000. Okay, according to our law, what we are doing here is that I'm saying, okay, delta E equals to negative WNC, okay, and so E final minus E initial equals to WNC. So I try to find out how much money I have here. I know initially I have 5,000 plus 1,000 in terms of in my account, in terms of mechanical energy, and then I deposit 2,000 here. So E minus this equals to 2,000. Then you do the calculation, you will find this equals to 8,000. So that's give us a way to calculate how much money you are going to have this month after you make some deposition. So the idea, basic idea here is that all these equations are quite straightforward. They're just the most simple algebraic calculation you may have, adding and subtracting quantities. Okay. But the important thing here, you have to be able to identify which equation you're going to use. So by analyzing the physical situation, you have to know, okay, this month, did I deposit some money, or did I withdraw some money, or I simply transfer money from between the saving account or checking account. So you are going to know which equation you can use here. Okay. So now, and here, another thing I would like to talk about is that you can see the relation between the three equations. These equations are simply a special case of this one. Okay. And another thing I would like to mention is that these two equations are actually equivalent to each other. So usually, it's just a different way to express the same thing. How can we know that they are equivalent to each other? Let's start with one equation. The first equation, kinetic energy, the work energy theory. You have delta K equals to W net, right? Okay, and the net force contains all the forces, including the conservative force and non-conservative force. Now, if you write the net force separately, so I can write it as WC plus WNC. Okay, so the net force will come from two parts. The work done by all the conservative force and the work done by all the non-conservative force. Okay, so I just rewrite it. Delta K equals to this one. And then I'm going to put this to the left-hand side. So I'm going to get delta K minus WC equals to WNC. But by definition, what is negative WC? It's delta U, the change in the potential energy. So this can be written as delta K plus delta U equals to WNC, right? On the other hand, by definition, the change in the kinetic energy plus the change in the potential energy is the change in the total mechanical energy, right? So delta E equals to WNC. So this equation is actually equivalent to this equation. It's just how we are going to deal with this term. Here I deal it in the work. Here we deal it in the mechanical energy. Now, let's look at the some actual example of this energy conservation relationship. Okay. So, one thing we can see is that if I drop this form, it will bounce back. Okay. The final position may be lower than my initial position, right? In this case, it just reached here. Or it can be almost to the same height of my initial position. But it will never higher than my initial position, okay? That's due to the energy conservation. If there is no energy loss due to the work done by the non-conservative force, then it will bounce back to the initial position, right? But, of course, in any real situation, you may have energy loss. when it hits the ground. Okay, so so it will be lower than the initial position. And throw it hard is try to reduce the energy loss at the ground, so it can reach the initial position. So in the case when it goes back to the initial position, the spatial equation can be applied. The mechanical energy is the same. Okay? And otherwise, the change, the mechanical energy, changing the mechanical energy given by the work done by the non-conservative force. And another thing I would like to mention is that the energy conservation, okay, think about we have a perfect situation. There is no air resistance. There is no energy loss due to the hitting the ground. The energy is conserved. Mechanical energy is conserved. And this conservation not only applies to the very beginning point and the very final point from here to here. It applies to any point during the motion. Okay? So what happens is that compare the point from here to here. So at this point, compare the point from here to here, at this point, you have a large potential energy, but zero kinetic energy. I'm not releasing it yet. But at this point, it has a smaller potential energy, but it has a larger kinetic energy. Okay? So there is no energy loss from here to here if you ignore the air resistance. It's just simply part of the initial potential energy has been transferred to the kinetic energy. So as it going down, more and more potential energy will be transferred to the kinetic energy. So why it's getting accelerated, getting faster and faster. Okay. And here,
without any resistance, right?
in this, okay, when I ignore any resistance here. Otherwise, there will be some slight loss of the total energy. Okay.
So if there's no mechanical loss at any point on the interval, it's going to have the same energy, right?
Can you say again?
If there's zero mechanical loss at any point on its path, it's going to have the same energy.
Yes, by definition, you don't have mechanical energy loss, and mechanical energy must be the same. But you just take different form.
Yeah.
Okay, so kinetic energy and the potential energy. Now, I would like to do a demonstration for the pendulum. Okay. For the pendulum, again, according to the mechanical energy conservation, it tells us if I release it from some height, it will go that way and back, but it wouldn't be higher than my initial position, right? So if you believe this kinetic energy conservation, so I'm going to do this. Release it from here. It will go back and it almost hit my jaw. Okay, but if I believe the energy conservation, I would say can never hit it. In my jaw, right? Do you believe it? Anyone believe it and would like to try it?
I would like to push it. Why you stand there? I like to push it.
No, you cannot push it, of course. You already understand that here. You can only release it from the wrist. Okay. Of course, that's the key. But let me check. Are we going to keep that?
I would say
So probably, I think they should be looking to a better place. How can I do this demonstration?
Yeah, that way.
Okay, this way.
watch out.
Maybe I should wait.
Okay. Okay, I got a problem. I don't have enough room to hit my jaw. So, okay, I can do something else. Huh?
Do it from the wall.
No, because that's very easier. So they put it in the wrong place.
Release it from the wall and see if it'll hit the wall again.
War? I don't want to destroy my...
Yeah. Well, do you believe in conservation?
Okay, you can do it, release it from a lower position, okay? And...
It's not as fun.
yeah, it's not as fun. So let's think about.
That's a
Yeah, it's catching up there at the top.
Where's the lab? Where's your lab?
So, unfortunately, will not be that fun. Okay. Okay.
Are you doing an analysis? Are you doing an analysis of force analysis?
No, just try to see what is required. I think you should be able to pass that, right?
Yeah, that'll be good. It's great, that video of it, in case anything is bad.
Could be fun.
Yes.
Okay. You don't like to stand here. You trust the size. Huh? Like to do that? If you really feel scared, you can just out to behind. So you don't have to say. You don't like it here? I'll do it. Okay, come here.
Push it
Don't push it.
Don't lay forward.
Okay, so you can release it. Try not. Right, use your head. You need to toss it. Okay, do it again.
Don't lay
Okay. So it's scared, but if you really believe it, it wouldn't hurt. Okay. I will leave this here. If you can try it later. Now, what we are going to call is that, okay. So